Instructor for this course. Welcome back. Today we're going to talk about independence and the multiplication rule. So in the last section we talked about what happens if you have two events that you can do one or the other or both of those two events. What would that do your probability? Today what we're going to look at is what happens if I want to do two things or more. What if I want one thing to happen and something else to happen? Okay, or what if I want these three events to happen? So that's what we're going to look at. So you can go ahead and take out your lecture notes to follow along. Once again, these can be found in Blackboard or my math lab, depending on your course structure, and hopefully it'll load here in a second. I don't know why it's not changing over to the other camera. Like it has every other time. Okay, there we go. So, whoops, and now I just put it back, so it'll probably take forever. Okay, so here we go. So, two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in the probability of experiment affects the probability of event F. So what this means is two things are independent if they don't affect the probability of the other one, and they're dependent if they do. So for example, dependent, if E were to happen and that changes what the probability of F is, then that would be dependent events. So to give you some examples, independent events, things like flipping a coin, that's independent because it doesn't matter what happened on the flip before that for the second flip. Dependent events could be drawing names out of a hat. If you have like 10 names in a hat, the probability of any one of those getting selected on the first draw is 1 in 10. But then if you take that name out of the hat and you only leave behind the 9 other ones, now you have dependent events because now the probability of any of those getting selected is 1 in 9. Versus if I put the first name back and it could get drawn again, then those would be independent. So one of the words you'll hear a lot of times with these is with replacement, which would be independent because if you're putting whatever you took out back, then the probabilities don't change. And then the other option would be without replacement. Okay, which would mean those would be dependent. Because if you're taking something out and not putting it back, now there are fewer options to choose from, so the probabilities of an individual thing being selected go up. So in this section, what we're going to look at is, well, what about for independent events? And then we'll talk about the general multiplication rule in the next section. So if E and F are independent events, then the probability of E and F happening, so the probability of event E and event F happening is the probability of event E times the probability of event F. This can be extended to any number of independent events. So if you want a bunch of stuff to happen, all of it to happen, then that's going to fall into this category if they're independent. So an example of this is, what is the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? Okay, so the probability of 4 ones would be the probability of a 1 and a 1 and a 1 and a 1, right? Because I need to get a 1 each time. So then those are independent, right? Because each time I roll the dice, there's an equally likely chance of getting any of the results. So then that means we could use our rule. This would be the probability of 1 times the probability of 1 times the probability of 1 times the probability of a 1. Okay? And so if we're rolling a 6-sided die, the probability of getting a 1 is 1 out of 6. So this would be 1 out of 6 times 1 out of 6 times 1 out of 6, which is 1/6 to the 4th power. Okay, so then we can do that calculation. And that is 1 in 1,296, or 0.0008. Okay. And notice there's kind of a second rule that goes along here with independence that we could notice in this problem, which is if I want to know the probability of doing the same thing over and over again, if I want to know the probability of n trials of an independent event, E, then it's simply the probability of E to the nth power. Okay? So on that basis, we could do this next one. What is the probability of obtaining 5 heads in a row? Well, flipping a coin, like we said a moment ago, is independent because you can flip heads or tails either time. What happened in the previous flip does not affect the current flip. So we would simply do the probability of getting a heads, which is 1/2, and then we want to do it 5 times, so to the 5th power. So that's 1 out of 32. Okay, so that's the basic idea of independent events. So let's look at some more examples. So among Americans who consider themselves auto racing fans, 59% identify NASCAR stock cars as their favorite type of racing. Suppose that 4 auto racing fans are randomly selected. What is the probability that all 4 will identify NASCAR stock cars as their favorite type of racing? Okay, so that's falls under the exact same idea of what we just did, right? So we know the probability of 1 NASCAR fan. Okay, so 1 fan is 0.59, 59%. So that means if I want to know the probability of getting 4 of those in a row, like they all have to be yeses, they do like NASCAR, that would simply be, so the probability of 4 fans would just be 0.59 to the 4th power. Which is 0.1212. So there would be about a 12% chance that if you randomly selected auto racing fans, they would say NASCAR was their favorite version. Now, along with this idea of these of the multiplication rule comes the idea of at least probabilities. So what is the probability that at least one will not identify NASCAR stock cars as his or her favorite type of racing? Well, the word at least, as we've mentioned before, means that many or more. So we want to know the probability that at least one will not identify NASCAR stock cars as his or favorite type of racing. Well, this is a good place to use the complement rule because let's look at all the possible outcomes here, right? We could have, let's say, if they're a fan, yes or no. So how many could I get? If I survey 4 fans, what are my options? Well, I could get 4 yeses and 0 no's. That's one possibility. I could get 3 yeses and 1 no. I could get 2 yeses and 2 no's. I could get 1 yes, 1 yes, and 3 no's. Or I could get 0 yeses and 4 no's. And all of the different ways those could happen, right? Because there's a few different ways you could get 3 yeses and 1 no. You could get 3 yeses and then a no. You could get 2 yeses, 1 no, and a yes. All those would fall into that category, though. So the question of these is which one of these categories fall into at least one will not like NASCAR stock cars as his favorite type of racing. So one of the ones that have at least one that is not a yes. Well, that's all of these. So I could, to find this, try and find the probability of all of these. But since we know all these are the outcome, we could simply use the complement rule. The probability of one or more is equal to 1 minus the probability of none. Right? Okay. That's a general rule that we learned earlier with the complements. So in this specific case, the probability of one or more not, or one or more no's, would be equal to 1 minus the probability of no no's, right? And this probability of no no's is the same thing as the probability of 4 yeses. So it'd be 1 minus the probability of 4 yeses, which we did up here, right? So this would be 1 minus 0.59 to the 4th power. Which is 0.8788. Okay? So that's the idea of what we're at least. So anytime you hear the word at least one, most likely the best way to deal with it's going to be to do the complement. Because the complement usually will mean only calculating the probability of none instead of calculating the probability of all of those. So let's go ahead and try a couple more of these together in the same problem, and then we'll go from there. So then it says, what is the probability that none will identify NASCAR stock cars as his or her favorite type of racing? Okay. So that would be none would mean we'd need the probability of 4 no's, right? So that's the probability of a no to the 4th power. And the probability of a no is the same thing as 1 minus the probability of a yes, which is what we know, right? We know the probability of a yes is 0.59. So that would be 1 minus 0.59 to the 4th power. 1 minus 0.59 is 0.41. So this would be 0.41 to the 4th power. So that's 0.0283. So about a 3% chance that if you randomly selected 4 racing fans in America, that none of them would be NASCAR stock car fans. Okay, and then the last one says, what is the probability that at least one will identify NASCAR stock cars as his or her favorite type of racing? So the probability of 1 or more yeses is the same thing as 1 minus the probability of 0 yeses, right? Which is the same thing as 1 minus the probability of 4 no's, which we did up here. So this would be 1 minus 0.59 to the 4th power. And you could type that whole thing in your calculator, or you could just subtract the answer from above. And so for that, I get 0.9717. Okay, so there's a few examples of independent events and using the complement rule to do at least one probabilities. So at this point, what I'd like y'all to do is flip over to the next page and try the 4 problems here. Okay, so go ahead and pause the video for a minute, try these, and then when you hit play, we'll go through them together. Okay, so we know that 29% of 21 to 25-year-olds have said that they have driven while under the influence of alcohol. Suppose that we select 3 21 to 25-year-olds at random. What is the probability that all 3 have driven while under the influence of alcohol? So that's the probability of 3 yeses. They have done it. So that's the probability of yes to the 3rd power. Probability of yes is 0.29. Right, because that's how many said in the survey that they had done this. So 0.29 to the 3rd power is 0.0244. So then what's the probability that at least one has not driven under the influence of alcohol? So that's the probability of 1 or more no's, right, which is the same thing as 1 minus the probability of no no's, which is 1 minus the probability of 3 yeses, which we just did up there. So that's 1 minus 0.29 to the 3rd. Which is 0.9756. Okay, and then what is the probability that none of the three have driven while under the influence of alcohol? So the probability of 3 no's is equal to the probability of a single no to the third power, which is 1 minus the probability of a yes is no, right? Because those are the complements of each other. Your only choices here are yes or no. So that would be 1 minus 0.29 to the third power. Which is 0.3579. So if you randomly selected 3 21 to 25-year-olds at random, you only have about a 36% chance that none of them have driven while under the influence. And then what is the probability that at least one is driven while under the influence of alcohol? Right? So the probability of at least one means one or more yeses, which is the same thing as 1 minus the probability of the complement, which is no yeses, which is 1 minus the probability of 3 no's, right? That's the same thing. So we did that one up here. So that's 1 minus 0.29 to the third. 1 minus 1 minus 0.29 to the third. So 1 minus. And that is the complement of the answer we just got, which is 0.6421. Okay. So now we've talked about using this rule a little bit and the idea of at least one probabilities. Let's go ahead and look at the last couple problems here, which are just some applications of this idea. So for a parallel structure of identical components, the system can succeed if at least one of the components succeeds. Assume that the components fail independently of each other and that each component has a 0.15 probability of failure. Would it be unusual for one component to fail? What about two components? Well, for one component to fail, that's a 0.15, right? The probability of one failure is 0.15. That is greater than 0.05, so that would not be unusual. Okay. So what about the probability of two failures? Well, the probability of two failures is the probability of a failure to the second power, right? Because they fail independently of each other. So this would be 0.15 squared. So 0.51 squared is 0.0225. So that's 2.25%, which is less than 5%, 0.05. So that would be unusual. Which when it comes to components, when it comes to a machine failing is a good thing, right? You want them to succeed. What is the probability that a parallel structure with two identical components will succeed? Well, for it to succeed, what that means is we need one or more success, right? Because it says in the problem that all of them have to fail for it to succeed. So we only need one or more of these to succeed. So that would be 1 minus the probability that they all fail. So no successes. So that would be 1 minus the probability of two failures, which we already did. So that would be 1 minus 0.0225, which is 0.9775. So if you had two components in this situation, even though they each individually have a 15% chance of failure, you have a 97.75% chance of success with multiple components. Okay. So then this one says how many components would be needed in the structure so that the probability of the system will succeed is greater than 99.99999. Okay. So what we can see is that with one component, the chance of success is 0.85, right? Because the chance of failure was 0.15, so success would be 0.85. With two, it would be 0.9775. And what we're basically doing here is we're taking 1 minus the probability of failure, which is 0.15 to the number of components power. So we could just keep building here. We could just through guess and check. So 1 minus 0.15 to the third is 0.9966. So we haven't gotten there yet. So then let's try 4. So 1 minus 0.15 to the fourth is 0.9995. So we still haven't made it to our how many we want to get to. So let's try the fifth component. So if I try 1 minus 0.15 to the fifth power, I get 0.99992, which is greater than 0.999. So the answer would be 5. You could, okay, so that's how we could do that kind of through guess and check. Just keep building up till you get the right answer. You could also use a little algebra here. So if you've taken college algebra or a similar class before, you've talked about logarithms. And we can actually solve this equation using logarithms if we wanted to. So let's just show how to do that real quick. So we set up the equation. We want 1 minus 0.15 to the nth to be greater than 0.9999. Right? That's what we want to have happen. And so now we just need to solve for n. So to solve for n, we subtract 1 from both sides. Okay, so that gives us negative 0.15 to the nth is greater than negative 0.0001. Divide both sides by negative 1, so you get 0.15 to the nth is less than, because remember when you divide both sides by a negative, you have to flip the inequality, 0.0001. And then we need to do, this is where the logarithm comes in. N is let's not use the inequality. We can just use equals here. So I think that's just going to mess with this. But then we get log base 0.15 of 0.0001, and we see what that is. And to put this in your calculator, you can go to algebra, and then you should see log sub b, and then it allows you to type in your base and what goes inside of it. And when you do that, you get 4.855, which you have to round up to 5, right? Because you can't have a fractional number of components. So there's a little way to use algebra to help us solve this problem too, but you can easily just do it by guess and check. Just keep increasing the number of components by 1 until you get an answer that's greater than 0.9999. Okay, so at this point, to finish off the video today, why don't we pause the video for a second? You guys try this problem, and then once you're done with it, we'll go through it together, and that'll be it for today. So now that you've had a chance to try this problem, let's work on it together. So suppose that a company selects 2 people who work independently inspecting 2x4 timbers. Their job is to identify low-quality timbers. Suppose that the probability that an inspector does not identify a low-quality timber is 0.2. What is the probability that both inspectors do not identify low-quality timber? Okay, so that's just, they have a 0.2 chance of not identifying it. There's 2 of them, so we raise it to the second power, and we get 0.04. So there's about a 4% chance that neither of these inspectors would notice some low-quality lumber. How many inspectors should be hired to keep the probability of not identifying a low-quality timber below 1%? Well, same idea as up here, right? We can just keep solving this until we can just keep plugging in. So we start off with 1 inspector, that's a 0.2 chance. 2 inspectors is 0.04. And then we could do 3, so that would be 0.2 to the third, which is 0.008, which is less than 1%. So there's our answer, 3. Once again, we could do this with logarithms. If I set 0.2 to the third equal to 0.01, which is 1%, and then I can solve using logarithms. Or not 3, sorry, n. I can just use the formula in general. So this would be n equals log base 0.2 of 0.01. Once again, you don't need to do it this way. You don't need to remember logarithms for this class, but if you do, you can do it this way. So that's 2.86, which when we round up gets us to 3, just like in the previous problem. Okay, so that's it for today. Thanks for watching this video. As always, if you have any questions, feel free to email me or send me a remind message, and I'll help you out. Don't forget to do your homework assignments and quizzes. And that's it for today.